let me try again. Hello, everybody. This is Larry. I'm in Laos right now. Missed the last contest, so I'm going to try to do a quick one right now. Weekly Contest 180. I think that's the one I missed. Yep. Okay. Let's go. Take a look. Wish me luck, I guess. Doesn't matter as much. So there's a little bit spoiled of the leaderboard. I'll try not to look at it. Okay. All right, y'all ready? Okay, I guess I'm ready. That's the more than fun. Huh? Hey, what up? Nice of y'all to join me. All right, let's go. Well, I have to click on stuff. And here we go. Let's see. All right, let's see. The first one, I actually had a little bit, I think I was proving stuff in my head. I was wondering whether, when I first looked at this problem, I was wondering if there's some sort of independence between the rows and the columns and whether you can kind of use that to your advantage and just do it in a linear way. I think you actually don't need to. I just kind of, I don't know. I think there's some intuition there for sure, to be honest. But I think that if you had just done an n to the fourth solution, that would have been fast enough. And it's not actually even n to the fourth, it's n to the third, because you just go, for each cell, just look at the column and then the row, so that's n to the cube, right? And that's way fast enough. But I think I was trying to be a little too clever, probably, maybe. And it turned out to be correct, but it could have maybe easily not been. So I don't know if I recommend that. But basically, I independently look at get the minimum, and this is true because all elements in the matrix are distinct. But if an element is, if a number is both the min on a row and the max of a, I forget which way it is. Well, either the min of a row and the max of a column, and they are on the same thing, then yeah, we put it into an array, and that's pretty much it. Yeah. I wonder if there's I wonder if you can have multiple answers. I actually didn't even check that. I guess I probably can. Maybe. But yeah. Well, that's pretty much what I did. If it matches, then return it. I had a small typo where I start off the min at 0, so of course it was not returning anything. I was like, huh, it's not returning anything. That's not crazy. Oh, this min as well. Yeah, once I ran the code and everything matched, I just submitted. I probably could have been a little bit more careful, to be honest, but it's a little bit of a virtual contest, so I didn't really think about it that much. This one, design a stack of increment operation. So this one just had a lot of reading. And also after the reading, it's a little bit tricky to read the output correct. So those are the two things that were a little bit tricky about it. But I think this particular problem was a case of reading the constraints of the problem correctly, because you can definitely play around with the increment function to kind of do the math in an easy way, or not easy way, just like to basically, yeah, there are ways to optimize it, I believe, but because of the constraints of the problem, you don't have to. You can just do brute force, because at most increment will run 1,000 square, which is 1,000,000, which is fast enough. But yeah, otherwise it was pretty fast, because everything is straightforward. You have to use your language's stack implementation, and it should be good enough. And you just have to keep track of the max size stuff. But yeah, and I think I had to reread it just in case. And this one is a little bit scary, I want to say, because it's easy to make a mistake. because you don't. I mean, it turned out that the input is good, or maybe good enough anyway. I don't know if it's good, but you can't really assume that I was just a little bit like I was a little bit what's the word? Yeah, I was just a little bit arrogant maybe, and be like, this is probably good enough. I don't know if I recommend that strategy. Yeah, but I don't think there's any tricky part of this problem as a result. Oh yeah, and I forgot to check the size of the stack to pop. That's pretty much it. Check to see what to return. Negative one. My God, that makes sense. And then once I kind of looked at the and it matched the output so I submitted it. That was pretty quick. Balance a binary search tree. I think with this one, this is one of those things where when you know a little bit too much, or at least for me. I mean, some people are very good at separating things, but for me, as a result, I was like, okay, I immediately think about the web black tree and stuff like this, or different ways of kind of balancing a tree, and I was like, oh, they have to implement rotation. I think in my mind, I was doing like, okay, let's find the root, and then like maybe do some like rotating the root up, and then like check to see if the depth is the left and the right, and if the left is bigger than the right by too much, you do some like correction there. So I was thinking along those lines for a while, and I'm already a minute in, and I was like, that can't like, I don't know if I was thinking that can't be it, but I was like, that's really complicated. I try to figure out like if there's a easier way, or just thinking about it in general. So then I skipped ahead. So I only took a minute to skip ahead. And here, when I read this, I was like, okay, this seems tractable. I was just reading the problem to see. I think I didn't really. It took me a little bit of time to understand what performance, which is the return value, how is that calculated. And once I did it, got a little bit easier because that's the problem. And yeah, and I think reading the example, they actually did a very good. I would say that a lot of props to the Leetcode writer for this, at least this problem. I mean, maybe the other problems too, right? But it didn't stand out, or I just didn't like I YOLO'd on that problem. But this one, I was like, oh, they explained it very well. Because after reading the explanation, I read the problem all the way to the last sentence, but which I was like, okay. And I think and at this point, or maybe a little bit later, but not that much later, I looked at n to see what the n is, and n is 10 to the fifth, which is 100,000, which is so at that point, I know that I need a linear algorithm or an n log n algorithm or something like that. So like n squared isn't going to cut it. That was kind of my point. Can I even do an n squared? Probably, maybe. I don't know. But I was just thinking about it. I think at this point, I was actually just trying to thinking. I thought about like, okay, efficiency is from 1 to 10 to the 8th, right? So there must be. I mean, this is what I'm thinking. I don't know. I don't think this is true, but so I was thinking like, okay, maybe there's some binary search or ternary search type, like some kind of search where, okay, for a given efficiency, what is the max speed that you could give me, right? And I think that I think you can get an answer for that question, but there's no like moving from one efficiency to another efficiency. I wasn't able to draw that connection to reuse sub-problems, if you want to call it that, but I'll just like reuse the state of the world in a incremental way. And I think for this problem, I was just thinking about, and I think I spent a couple of minutes thinking along those lines and try to think about the invariance of the problem and just try to figure it out. Look at the second one, and I was just trying to figure out like, because it's the same, and I was like, okay, does k, like, I think at that particular instance, I was thinking like, okay, does the k equals 3 solution build on top of the k equals 2 solution? Like not quite exactly, but some sort of like dynamic programming thing. Not a dynamic programming problem, but just that kind of thinking where you're like, okay, here's what we solved. Can we build on top? Like, is there an answer for k equals 2? And then now for k equals 3 is this other thing that is just like one, like maybe it takes log n to build on top of that, and then that's how you get to log n. But I couldn't figure it out, and also you might have noticed I put the mod there just so that I won't forget it. But as you may find out later, I forgot it anyway. So always forget the mod on this one. But yeah. Which is kind of sad because I thought about the mod a lot, but I think I was just too deeply in the problem. But yeah, I think at this point I was maybe leaning toward a heap because it reminds me of a problem about I forget what the name of the problem is, but maybe I'll link below, something like that. The similar problem, but it did remind me a little bit of a problem, and I was trying to figure it out, and I was trying to also figure out if there's some sort of like maybe there's a speed over efficiency ratio type thing that I could take advantage of. But so those are the lines that I was thinking of. And then first of all, I was like, okay, I need to sort by efficiency and speed, and that's what I did by sipping them. And then I was like, okay, it probably makes sense to sort by the efficiency from the highest to the lowest because the state is such that when you add in more, when you add less efficient things, everything that was already true, the invariant is that everything that was smaller than, or has an efficiency that's higher than x, for the index after that, it'll be all those, all the speeds will have that efficiency plus the new one you add. So that was kind of I thought about it. And for that, I used a heap, and I was trying to think. I think it talks out loud here. Trying to figure out like, okay, I mean, I knew I need to use a heap, but how do I use a heap, right? I was like, maybe I could just use the n log n heap. But then I was like, okay, no, they give you the k, so you want the k, you want one of the k heaps. And the thing that I always think out loud a little bit about is whether I use a min heap or max heap. And then here I think about, okay, you want a min heap because you always want, whenever you put in something, you want to remove the min so that everything inside is the max. So that's the invariant, is that everything inside the heap is the max thing that you have. And then I think at this point, I was like, okay, so everything inside the heap, we just want the sum of that times the yi, right? And then here, I took advantage of the fact that, addition is linear and stuff like that, so that I could just kind of make this way more efficient as a result. And that's pretty much this problem, except for one thing, which you'll see in a second. Sad face, crying Larry. Well, that's the other thing.
For not practicing in a while.
Me not being as practiced enough, I just forgot some brackets. I was like, no, that doesn't make sense. So that I spent probably like a minute about it on this, just being dumb, because I think I Googled this a little bit as well, which is really unfortunate. But that's what happens when you're rusty. That's fine, because I am traveling a little bit, so a little bit of rust is to be expected. This is the only coding I do in about every week, and I don't even do that much. Maybe I should have warmed up actually, but that's fine. This is a virtual contest, but yeah, I was just like, oh wait, do I need to make them a tuple? I think right now I was good. Also, because I put it, that's the one thing about snappy one-liners is that when you get a stupid error like that, you don't know which part of the one-liner is having issues. So then I was like, okay, actually that doesn't make sense. This needs to be a tuple. So then yeah, and then I know that that was just an input thing. I just need to clean up the input. Sanity test. 60, 68, okay. Yeah, I was seeing 60 and 68, so I was like, okay, that's good. That's a good, signal. Let's at least test the last one. I didn't notice that they were the same numbers until just now, but I submitted hoping that was right. I was like, oh no, wrong answer. Why is that? And I was doubting my algorithm a little bit, but I was like, oh no, I returned a big number, so I probably just forgot the mod. Test it just in case, obviously, because this one is easy to they let you copy and paste, so that's easy. That's pretty silly. So then yeah, actually. And then I submitted, and then I was like, hopefully that's right. Okay, good. Silly mistake. But luckily that wasn't a real thing. I wasn't happy about that one, but that's it. It is what it is. And then now binary. That's why I put it on the top, and I forgot. Anyway. Balance a binary search tree. Okay. Yeah, I mean, I think at this point I was still on the rotation E way of solving it. Yeah, like web black tree or something like that. And here, and from that, I think I start to go along those lines a little bit. I was like, okay, you just have to do it, right? Sometimes you do things the quick way, sometimes you do things the long way, and sometimes you just have to do it. So I was trying to figure out, like, okay, let's, my algorithm. I mean, I know that this wasn't right yet, but I was like trying to figure out how to figure it out. I was like, okay, well, if the depth of the left tree is not within one of the right tree, given some signs, then if it is, then it's good. Otherwise, I have to do some magic things, right? So that's kind of what I started on working for now. That's not even true. That should be an integer. I don't know. I think I was just really not thinking about it at this point out. Well, the depth I could write on my sleep, except for apparently not. But yeah, but as I was trying to write out, I was like, okay, well, we probably need the actual numbers to kind of see the rotation. So let's do this so that we don't calculate it twice. I think while I was writing this, I had a stroke of like, well, I look at the number of nodes, I was like, oh, 10 to the 4th, huh? And they're all distinct values. So, and at the time, to be honest, I didn't know if that was, like, I felt like that was a little bit not in the spirit of the problem. I thought maybe you have to do it in place, which is why I struggled a little bit for this one. But then I was like, oh wait, I guess that's it. But I wasn't sure to be honest. So I still take a couple of minutes. But other than, I think in theory, once I did that, it only took me about 3 minutes-ish to program and to code it out. Probably could have been faster still, but I wasn't really sure. I mean, I think I should have just been faster. I mean, this this is something I should be able to do in my sleep, because we do so many tree problems. But yeah, and note that you can actually, so this requires sorting, which is n log n, but you can actually, if you're careful, you can actually just do an in order sort for obvious reasons and keep it O of n, but with 10 to the fourth, which is n, which is what, 10,000, n log n is not going to be an issue. So yeah, and then now I'm like constructing a tree. I was like, okay, let's just take the middle element. I'm trying to think of the name of the function actually. That's why I was struggling a little bit. I think in my mind, I knew what I want to do kind of. It's still very vague, but I didn't do it yet. I was trying to figure out what it means, but now construct the left and the right. Yeah, and then I was like, okay, actually you need the left and the right. I was also just thinking a little bit right now whether you're going to get some weird scenario where, because this divided by 2 always truncates, so I worry that there'll be too much to one side or the other. That's what I was thinking about, but I was like, no, even in the worst case, which is probably like power of 2 minus 1, it should just be at most 1. It would just be like a very weird looking tree, but it would still be balanced. And then I just had to do the base case, and that's pretty much it. I was kind of, I won the code, I was like, oh, this is not the right answer. Yeah, well, I mean, that's also not the right answer because I used the wrong function. Yeah, and I was like, oh. Just another base case. I was like, oh, those answers are right. Why am I getting 2 4s and 2 1s? But it's just that I didn't index correctly. But that's pretty much it for the commentary. Thanks for joining us, and hopefully see you next week or next video. Bye-bye. Or talk to the other Larry. That was kind of a weird problem, but okay, let's take a look. I didn't do that well that time, but that's okay, I think. That was a good practice, I think. That was a silly 5 minutes. That's one. Let me take a look. How did I do? Is this fine? I don't know how often this gets updated or whatever. But that actually, I would have done pretty okay. I mean, obviously that was a really silly mistake, but other than that, and if I didn't make, that was such a mod error. But if I didn't get the mod error, I still would have not been top 25, but it would have been close. I've been 26. So 26 to 36, that's pretty okay. I think that's all you can ask for not being in shape. And also a little bit of a good comeback from last round where I was like 200 for something. Okay. That's I'm just going to go over the problems real quick and then can have a little bit chat. And the problem is you can't really code review until everything is done for some reason. But Yeah. Okay. Lucky numbers in a matrix. Yeah, I think the thing that I actually took a ow, I scratched myself a little bit too much. Um, yeah, not many fast solutions. I think people were trying to. I mean, okay, 2 minutes is pretty fast to be clear, but usually there are a lot of people that are just really really fast and they finish in like 1 minute. And I don't know if there's any contest specific things. I don't know, but so I don't want to look too meta about it. But this one was a little bit trickier for me to kind of. I think for me there are a couple of things that I have to prove correct in my head. Um, but I think the fact that because they were distinct, that allowed this condition to be easily true. Because otherwise, you might have to. Actually, maybe it's still okay, but it's just like a little bit awkward. Um, but what I did was I just keep track of each row as the min and the max, and then after everything's done, if they're equal, then that fits the condition, and then that's good enough. Um, I think also, to be honest, now that I look back a little bit, I was probably too clever on this one. Probably, I did an n squared, one pass, but you, now seeing more specifically that n is 50, you probably could get away with like an n to the fourth algorithm or something like that, which is maybe fine. But but yeah, that's what I have for this problem. Yeah, I mean, I think that's okay. I mean, I did it in 2 minutes. I mean, this one was even more straightforward. And I think a lot of people's timing kind of reflect that a little bit. I mean, they didn't, you know, because I think the constraints us in such a way that I think for me, I didn't know I had to do something clever for increment. And there are clever things you could do to kind of keep track of operations so that you could pop them in a good way. Um, but because it guarantees that there'll be only be a thousand of these. Oops. And since there can only be 1,000 elements in the max size, that means this is only going to have ever do 1,000,000 operations and square. So that's when I was like, yeah, that's actually. I mean, I was doubting myself a little bit because it almost feels too easy, to be honest. And I don't mean that in a patronizing kind of way. It's just, sometimes you're like, like this is really wordy for something that feels a little bit easy. Like this should be a trick, but I guess in this case that was not the case. Um, Balance a binary search tree. I do wonder how other people did it. I struggled a little bit with this because I thought you would, and maybe that's the that's probably the ideal case anyway. But I don't know how people do it for speed because, geez. Anyways, this is in 2 minutes or so or something like that. So with T will and stuff like that. Will Lin. So yeah. And I took way longer. I mean, even with this, I took 8 minutes because I was trying to figure out a way to, given this tree, like, like do a rotation like at a wet black tree or something like that. And I was like, but then I have to do, but then that's like hard. Or like, it's fine. I mean, it's not impossibly hard. It's just hard to do in 2 minutes because I haven't done wet black tree stuff in a long time. Um, but yeah, but I end up, I mean, one is I skipped ahead and then I came back to do it. Um, and yeah, and I just kind of cheated a little bit. I really don't know. I mean, it's a really ugly intended solution if that's the intended solution. But basically, I just took all the number, which just did a depth first search to get all the numbers, sort them, and then just take the middle node, like kind of what's it called, like quick sort or something like that, right? Where you have all the nodes, just take the medium element and then put that as the root and then so forth. And that's kind of what I did here. And if I had thought that way, I could have done it much faster, but I was just, I was just stuck on the idea that maybe I had to do some rotation or something like that. And that's really tricky, I guess. Um, Clearly, people are way smarter than me on this one. But maximum performance of a team. This one, to be honest, one is, I knew, this mod thing hurts a lot because it cost me 5 minutes. Which still, it's silly, it's unnecessary, right? Like, and I wouldn't say I knew it, but like I was like, oh, Larry, you're gonna forget this. Let's write this on top, and then I forgot it anyway again. But most of it because the rest of it was so easy, maybe surprisingly easy. I don't know how long I took because I took a couple. This looks like 10 minutes from Q2 to Q4, but I took a couple of minutes on Q3 before skipping. So let's say 8 minutes ish with the error, but the error was pretty quick to fix. So I got this pretty quickly. I think for my standards, because Neo in 8 minutes would have solved almost all problems, but I think in this case it is the cost. It reminds me of another problem that I've seen. I don't remember the name off my head because Leetcode problem names are very direct. But I was thinking about, well, at first I was thinking maybe some sort of binary search. Maybe I was like, okay, if, that's why I looked at 10 to the 8th, and I'm like, oh, if I do a binary search, then like, okay. Let's say the efficiency is 10 to the 4th. Okay, that's actually a terrible example. Let's say efficiency was, say, 5 for this, right? Then what do we want? Well, we want all the numbers here that is higher than, whose efficiency is higher than 5, and then given those, you sort it by the max, right? Because it's greedy in that sense. And I was like, can you do it that way? Is it and if you think about binary search, is it like monotonic? In this case, it's still like a sort of whatchamacallit. I guess in that case that would be a ternary search, and maybe you could do that too. I don't know. I haven't thought about it, but for me, I was like, okay. Well, another way that I was thinking about was a little bit more brute forcey, even though I saw that n is 10 to the 5th. So I was like, okay, what is the n squared way of doing it, right? N squared way of doing it is sort everything by efficiency, because for me, I was just trying to create an invariant in which everything inside something or held, there's some condition for which this is all true. So that's why I sort by efficiency going from highest to lowest, because in this case, if you go from highest to lowest, that means everything that's inside, like everything that you processed is already, like let's say your current cursor is at 5 for efficiency. That means all the numbers that are in speed that you already processed, they already have an efficiency bigger than 5. So then you could just multiply by 5, because in that case, that would be your current min, because it doesn't matter what the other efficiency are because they're bigger than 5. And 5 is the only one that care. So thinking from that, my next step was to be like, well, let's say 5 is the efficiency that you want. What is the max speed? Well, in this case, you just went like, and I kind of alluded to it earlier, you just want greedy, right? And then from that, I was like, okay, you have a set of, you want to keep a running set of max k numbers, and then you keep changing it depending on, and then you keep tracking of the max k numbers, and that is already maybe not very, but it is to me anyway. That's where the heap came from, and that's pretty much it. That's pretty much what I did. You could have. I want to say, I guess maybe not. I was going to say maybe you could have. I did this as a little bit of an efficiency thing, because I was like, maybe you need to sum this every time to get the max, to get the total. But I was like, but you already know what you're putting in and what you're putting out. So and because summing is, or addition is linear, you can do this, and it's what you would call it, associative. Yeah. So that's why I kind of did it this way, and then and that allows it to be n log k. Well, okay, it's n log k for this part, but this part is n log n, so it effectively is n log n. Still a little sad that I ate 5 minutes for this one, but it's okay. Lucky it's not a real. I mean, actually, it would have been okay if it was a real contest because I finished 36, but I would still be like a little salty about it. Okay, that's all I have for this contest. All right.